Hi everyone, my name's Stephen Cooper. I work with the Juniper Mist team. I'm going to give you some examples of how data science and automation can help solve some problems beyond the Wi-Fi access layer. Now, we all know we get blamed for the Wi-Fi being the problem more often than not. It could be VRF issues, could be VLANs, could be congestion upstream, could be radius issues. It's usually DNS, isn't it? So I'm sure you've seen that quite a lot of times. How often do we get blamed for DNS? So where else can things possibly go wrong? All the way from the Wi-Fi users that we're supporting through the network. We're not often responsible for end-to-end connectivity through these particular elements of the network, but anything anywhere could go wrong along here. And actually, Bob Friday is going to give you some more examples tomorrow of the visibility into the application experience side of where users can be blaming bad Wi-Fi. So as network engineers, as wireless engineers, what sort of tools do we usually have when we're starting to troubleshoot beyond good Wi-Fi? So let's say we've got great coverage, great signal-to-noise ratio, our clients are connecting well, but they're reporting problems. And so these are just some of the tools available out there in the marketplace. Highly recommend checking out the NetRLI session tonight because they'll give you some good examples of some of the cool things their tools can do around detecting wide network problems. But depending on the infrastructure you're using and your experience, you may or may not have some tools there to help you find these problems beyond the Wi-Fi access layer. And obviously, we've got things like the great WLAN speed test is very contentious as to whether that's a useful troubleshooting tool or not, but it is out there to use it too. And just some quick limitations on some of these tools is, the big one is it's usually only a single point in time that we're performing these tests and a single place in the network, not necessarily end-to-end, as I mentioned, where any of those problems could lie. And then when we're gathering this data and performing these tests, there's a lot of manual legwork, time on site required, manual data analysis, and understanding the actual root cause of the problem. So, how can we start to look at some of these models? I'm not going to go into detail with all of them, but just give you some examples of, as we go through more complex problems, you might need some more complex algorithms in your toolbox to help to automate and find those root cause problems, basically using some machine learning and deep learning technologies. So we'll go through some of these. But as you can see from this chart, the more complex these algorithms are, the more computational complexity that's behind there, the more computing power you require to do this. And the aim of the game is to get this information to you as network engineers as quickly as possible to get your users back to enjoying good Wi-Fi as quickly as possible. But also the increasing complexity can also provide better intelligence. So make your jobs easier to actually find the root cause of these problems easier than before. So I wanted to give you a quick example of a supervised learning technique called k-nearest neighbors. And I basically said, okay, let's just do the analogy of like a streaming service, recommending songs for you, whether you've liked particular songs before or not. I'm a metalhead. I went, okay, let's just search on stock photo for a metalhead. And this is the image that came up. A Latino woman apparently looking at the camera with the metal horn sign. She's not looking at the camera, she's got her eyes closed. So I decided to work around this using a tool, not by myself doing manual copy and paste of some eyes, but yeah, these tools are out there, as we know. You can make your job easier and make your life easier just by automating some of this stuff. So, let's say we gathered a collection of songs, heavy metal songs varying in tempo and speed and intensity, depending on what this person likes and doesn't like. So we've got a data set here circled in the top right of songs that this person likes and songs that they don't like so much. So the question is, can we then predict, if we introduce this person to a new song, are they going to like this song or not? So this is where we can start to look at some of these regression and classification models and say, there's a new song in there based on the tempo, based on the heaviness. Yes, this person is going to like it because it falls in that known data set that we've trained this model on, saying they're going to like this song. Now, if we have another song that's not quite so easy to determine, it sits there somewhere in the middle of tempo and intensity and mood, are we going to be able to determine, with a high level of accuracy if this person is going to like the song or not? And this is where, some of these models will start to do some sort of classification around this, group this, and k-nearest neighbors means we're going to take the nearest neighbors that weigh in favor of like or dislike, and you can see there's 3 likes within the circle versus 2 dislikes. We're going to say this person's probably going to like this song. So that's just a good example of how you can do that. Now, another supervised learning technique which we could actually use with network troubleshooting is actually looking at mutual information and the correlation of entropy from random variables and their relationship to another random variable. And what could these random variables be? Well, we could be looking at a metric, which could be coverage. It could be capacity on the network. It could be the time to connect to the network or complete DHCP or complete a radius authorization. It could even just be a simple pass-fail if we wanted to measure that. Did the user successfully connect to the network or not? And then we can relate that to features of the network. And those features could be anything from 5 gigahertz versus 6 gigahertz connection. It could be device type. It could be device operating system. It could be access point model. So we can get any of these information from the data set of the known network infrastructure that we have, as well as the users that are connecting to the network. And we basically want to find this correlation factor in the middle of how they relate to each other. So we can start to get some information of what depends on success versus failure based on these metrics. But what we want to really do is predict what impact that the metric has on the success or bad experience this user is going to have. And for that, we use a tool called Pearson correlation, which says, is there going to be a positive or negative impact onto this user's experience or the metric that we're measuring based on those network features. And in the real world, what this can correlate to is root cause analysis saying, we've got users having problems connecting to the network. They're yelling and screaming saying, we can't connect to the network, the Wi-Fi is down. But using mutual information correlation analysis with the data coming in from the network infrastructure, we can say, well, yes, only the Windows users are impacted because we've now got these mutual correlations showing the pass versus fail, success versus unsuccessful, saying, well, all the other device types are not having a bad problem. So we've got this correlation factor between that, and we can say, we need to take action, fix the certificates or whatever the problem is with those particular Windows laptops and get them back on the network. Another supervised learning algorithm is decision trees, and this is where we're basically iterating through different questions or if-then-else statements to try and get to a high efficacy or correlation factor of some particular impact of a root cause of the network. And one example I'm going to give you is around detecting bad cables. So yes, we could manually go on site and do some bad cable tests with link sprinters or any other cable testers that we have, but we can actually use the network infrastructure to do this as well by detecting and analyzing, is there framing errors? Are there MTU mismatches? Is there one-way traffic? Do we have a PoE pair working and the access point's powered up but the data pair is not working? And we can then use the decision tree to basically assess at each stage what is the certainty that we have at each node by asking these questions, and then we can use a feature called information gain to then determine which of these questions and the answers to these questions are reducing the uncertainty at each step of that node. And then we can say, okay, each time we've done an assessment against some of this trained data that we have the known outcome for, we can say, yes, that is a bad cable or not. And so, that helps us do that without running manual TDR tests on the CLI. That helps us do that without actually sending someone on site until we're 100% certain that we do need to send someone on site to fix that bad cable that's on the network. Another basically level up of decision trees is XGBoost decision trees, which is essentially multiple decision trees trying to even more quickly determine the root cause of the problem, but using multiple potential data sets informing that decision for the root cause analysis. So, you can imagine multiple decision trees with multiple inputs coming in, and a good example of this is when we're trying to determine if there's throughput impact to that wireless user's experience. Because we all know, on the Wi-Fi side, the factors that influence a user's performance or experience in terms of throughput are things like signal strength or signal to noise ratio, data rate or MCS rate, what the channel width is, and obviously what the device's capabilities is. But beyond that, the wired network, the WAN network, latency on that network, all of those things could impact what a user's theoretical throughput could be on the network. So we feed these metrics that have been learned through a large set of data from different users on different sites across different access points and use XGBoost decision trees to say, is this user going to have a good experience on the network or is there going to be a bottleneck? And this is an example of where there's a particular site that's been deployed, the Wi-Fi is perfect, the time to connect is perfect, the coverage is great, everything else is working well, but the LAN and WAN is the bottleneck here, and this, these users are only going to get about 1.4 megabits per second. So, someone's going to complain about slow Wi-Fi, but we have proof here, thanks to this machine learning algorithm, that it's not the Wi-Fi. Now, I'm going to give you an example of some unsupervised learning, and this is where we start to get into that really complex area of that chart and the more intelligence that then comes with those complex algorithms. So this is similar to that model that I gave you about classifying songs, because it looks similar, but it's actually completely different. this is actually automatically clustering data from known labeled data into specific groups. And this particular example is around determining if there's a missing VLAN causing user experience problems. So someone's connected to the wireless access point, their connection's great signal to noise ratio, but the traffic's going nowhere because on the wired network, on the switch port, that VLAN has not been configured, it's been missed, someone's fat-fingered a config, and this algorithm can actually determine this by automatically clustering this data through flow analysis of particular VLANs. Is it high traffic? Is it a low traffic VLAN? Is it a known quarantine VLAN that's been configured on the SSID, such as a pre-authorization 999? So that's fulfilling its job of actually black holing that. Or is it even an over-provisioned VLAN? Someone might have configured a VLAN across every single site, but it's not actually needed at every single site, maybe just 5 sites. So K-means clustering is a way of automatically classifying and labeling that sort of data. And it's often used for image classification, customer segmentation data to group customers, for retail use cases. It's used for banking and fraud detection as well. So it's got a lot of useful use cases just beyond networking as well. So it's used quite a lot out there. And then principal component analysis is basically helping improve the efficacy of this algorithm to get that clustering of the data. It basically minimizes any of the variance in here to get these nice tight groups of what this data is being plotted on there. So the benefit of this is, we can remediate this automatically depending on what the network infrastructure is that you have, or at least inform network administrators such as yourself saying, hey, there's a VLAN missing here. You're going to want to fix this before your users start complaining and blaming you for bad Wi-Fi, essentially. So that's a really good outcome too. And this is what it looks like in the Mist dashboard when we actually say, hey, you've got a missing VLAN. This is the switch port. If it's a Juniper switch, fantastic, easy to remediate. Ideally, if you've deployed this from day one using configuration templates, you're eliminating some human error. But for a third-party switching infrastructure, we can at least notify you for that too. So this is something we can detect even on third-party networks, which is a big help for a lot of our customers. The last one I wanted to give you is probably the most important one, or at least the most useful one, because we can all design networks and configure them and deploy them as best as we want to, but things always go wrong, and usually when we least expect it. So anomaly detection is where we can have some models learning the normal baseline of the network, determining what is normal for the realms of operations, and that might be different for all of your sites or different areas of the network that you're managing, and it can also be different depending on those different network elements. You might have your access points and your network running really well from the Wi-Fi side, the switching side might be really, really good, and then DNS suddenly starts to have increased latency and your users are complaining of slow Wi-Fi because your DNS resolutions are suddenly spiked up and taking a lot longer than they usually should. And that is something that's usually quite difficult for humans to detect by themselves unless you're staring at a dashboard 24/7 and some people love doing that, but I particularly don't. So, this is where the machines are doing that legwork for you. And this is an example of where over time you can increase the efficacy by applying different tools from a data science toolbox. And you can see going from moving average to ARIMA to long short-term memory recurrent neural networks to really get that high level of efficacy that you can find these without having false positives. That is another element which is made possible by data science and machine learning, is not saying, hey, there's a problem when there really isn't a problem. And you can actually then use this particular model not just for one customer or one tenant or one site. You can use this model that's been dynamically learning this across multiple sites to get the benefit across everyone. So an example here could be DHCP or Radius has suddenly started taking longer to complete, and we want to make sure that we raise that at least to the network operations team or your help desk, and it might not be yourselves that are responsible for it, but at least you can then escalate that to your infrastructure team or whoever's responsible for that service so they can stop blaming you for the Wi-Fi, right? That's the aim of the game there. So those are just some quick examples. There are a lot of other tools that you can use out there, a lot of other great people that are working in data science that know a lot more about this than I do, including my colleagues at Juniper Mist, but these are some of the examples that we've touched on around environment learning, decision trees, detecting bad cables. It can also be used for detecting issues with access point and switch health. So the same sort of concept, right? You're detecting bad cables based on some known outcomes based on the impact of framing errors. We all know that framing errors are bad, and we know that that's going to cause problems. We also know that high switch CPU is going to cause congestion and throughput problems on the switch. So we have all these problems that we know about. It's just there's so many things that can be potentially happening out there that we want to try and get on top of those quickly, as quickly as possible. So the examples that I gave you have all been models that have been trained based on user data with the users connecting to Wi-Fi networks, so using the Wi-Fi networks for 7+ years and training these models. And you saw this with the anomaly detection algorithm going through different iterations and trying to improve that efficacy. Now, what can we do with this now that we've actually got these models trained and actually baselined across different users' experiences? What we can then do is still use those same models natively with the network infrastructure without requiring users on the network. So let's say you deploy a new site, and it's all based on the configuration templates that you've used for hundreds, if not thousands, of other sites that you've deployed, and you don't have someone who's available to then go out on site and do your user acceptance testing or actually determine if that's all working as it should do. Well, you can use the network infrastructure to do that natively based on the same AI models that you've then been using to train this. And this is something that you can find out a bit more at our vendor session tonight. But it's essentially leveraging the same sort of data inputs into the same models that have been trained and learned in this over time, so you can find problems even quicker without even having users on the network. So you can then fix things before users are on site yelling and screaming, saying that the Wi-Fi is slow or they just can't connect. So recommend coming along to have a look at that. Also, some great useful links here as well. Highly recommend my colleague Sean Freeman's blog series down the bottom. He starts to go into a bit deeper analysis of what's going on behind the scenes of some of these algorithms. And we have a great whiteboard series and playlist which goes through some more examples of how these models actually work behind the scenes and what use cases they could actually be solving for you too. So highly recommend checking that out. Lastly, please come along to our vendor session tonight. And you have a choice. I don't envy you. You have to choose between Harmona or you have to choose between Juniper Mist, but one of them has alcohol, one of them has free APs. I know which one I would choose, but if you want to come along, if you want to run up, down, and stairs, you can do that to try and maximize the time between each session, but please pre-register. Just fill out this form, the QR code, if you want to come along and get a free AAP. If you don't get a chance to take a photo of this now, don't worry. Find one of the Juniper Mist team. We'll give you the QR code to fill this out, and hopefully we'll see you tonight. Thank you very much.